So as I was saying, now we've got three types of stress: normal stress, transitional stress, and bulk stress. So normal stress is divided into two types of stress. You know that when you apply force, let's say on a rubber band, no? If you are pulling, or let's say on a sponge, let's say on a sponge. Let's just say, for instance, this is a sponge, right? Let's say this is a sponge. Then if you are pulling it, that sponge, if you are pulling it, the force that you are applying is what we call tensile stress. And then if you are compressing it, if you are compressing your object, then we're talking about what we call what? A compressive stress. So now these are the two types of normal stress: tensile stress and compressive stress. So with tensile stress, the formula is the same as that one of stress, right? It's the same as the one for pressure of stress. The stress component is the surface of the body is loaded by, yeah, so the unit is still the same as that. It's still the same as sigma equal to force per unit area. So tensile stress, it will cause an arrow will be pulling, so it will cause an expansion. So tensile stress will be an expansion. So that's the important term there. And then with compressive stress, the object will be squeezed, since you will be squeezing it in. Then now, so there is no formula for, let me see. Tensile stress. So the formula for compressive stress is not here. That means it's the same, no? As that one. Well, let me see. It is a stress leading to the decrease in the length of a material. So will you guys will have to check if there is a formula for compressive stress. But I think if it's there, because since it's talking about the length of the material, it will change. So it's probably going to be sigma equal to changing L over L, right? It might be this one, but here you must go and check that. Then we have what we call tangential stress. Uh, so with tangential stress, the only thing that's going to change is what? We're going to have a change in the height of our object. So let's see how the formula is like. Just stress object is equal. So tangential stress has got two names. It's either we're calling it tangential or we call it shear stress. That's another name for tangential stress. So it's that equal to force tangential divided by area of our object. So this one is the book. This is a book, right? So they are pushing it to that direction. Obviously, there will be a change in what in height. As you can see, the height will change, and also okay, the length will remain the same, but the height is gonna change. So this one you can just say you can just realize that okay, the height is change is being will change, right? Just say it will change. So now go to stress. So the bulk stress, this one it affects the what by checking how much the object is undergoing, uh, how much the volume of our object is changing. So with volumetric stress, we're checking or focusing on the volume amount. How much is the volume being affected? You can see the rate at which the volume is being reduced. So that's what we're checking. So, okay, this is just the formula for pressure, right? The reason why including remember that there is a relationship between volume and what? And pressure. There is a relationship between volume and pressure. That's what we're talking about P. So now you will have to know the formulas, right? So down there, we're gonna talk about back strain. You'll see how the formula is like. Because I'm sure it's something like B is equal to P divided by, I think, the volume. Yeah, something like that. That will be our bulk modulus. We'll talk about something called modulus. So modulus. So we've got types of modulus, which we're gonna talk about. So now we move. So with this one, now we're going to the concept of strain, right? So the unit is what? Is that funny E? And then up there, I hope you guys you didn't forget that the unit for stress is represented by the symbol sigma. So you must not confuse the two because they're gonna give you formulas and then you confuse them. So you must know that this one is now checking the strain. So with strain, we're checking the change in the shape and the size of our object due to that deforming force. But with stress, we're only checking the rate at which the object is changing. So now the formula is saying change in dimension. This is the general formula, right? General. Now we move. So we've got types of strain, we've got three of them. We have longitudinal. This one is talks about what? The length. V, volumetric, volume. Even the names they are speaking for this S, shape of our object. Now we're focusing how much object is deformed in terms of length, volume, and also its shape. So with train we're making the rate at which the object is changing when we're applying our by actually checking how much the object is deforming, the difference between S and strain. Now let me see if I can actually since the amount of force being that's applied to express the changing shape. So if they ask you to differentiate, no? If they ask you to differentiate between stress and strain, this is how you will write it. Let me come here. Let's say they say differentiate the two terms, stress and strain. So with stress, you can just simply tell them that is the amount of of force per the unit area, whereas this is different, whereas strain is the deformation, or change. Let's just say it's the deformation. Yeah, now we're checking the point that when it now deforms. The deformation or change in the shape that the force being applied, let's just say the applied force causes in the object or material. And then we'll move to those types of strain, right? Now we want to check the first one, the longitudinal strain, which focuses on the deformation which produces a change in length. So the formula is it will be like this. Remember here the general formula for strain is change in dimension. So our dimension here is length. We're talking about the length. So A longitudinal strain will be given as change in L over L. So what you guys have to know now is just to apply these formulas. Because volumetric, because I'm explaining them, I hope they are not that difficult. Volumetric strain is change in volume over V, and change in volume, obviously, this will be V final minus V initial over V. Right, they even give you a box. This box is showing that if we're applying a force, there can be a change in the volume. The object can reduce. As you can see, this one is bigger, and this one is what? It's small. Now, that's why we're talking about the pressure. Then we're about to call shearing strain. Or shearing strain or tangential strain. Here, wherein is when the deforming force produces change in the shape of the ball. So we're talking about the shape, hence the formula would be like this. We're talking about both the length, yeah, actually we're talking about both the length and the height. Hence, obviously, if something is changing in terms of its length and as well as its height, obviously you are talking about the change in what? In shape of that object. So now the formula for shearing stress is given as what? Is given as tan. Let's use bright colors. It's given as tan of theta equal to change in length over the height. This L represents the height of our object. We just use L. You can also see change in X over H if you want. Right. Then if they want, and you guys, you can see that the unit for shearing strain is theta. So this is our shearing strain. So meaning that if they want it, you are going to say theta will be equal to the arctan of the change in length over the height of your object. Now move modulus of elasticity. Now we are talking about the modulus of elasticity. The first one is what we call the elastic modulus. It measures the stiffness of our material. How stiff is the material? We move. So the formula for that is what? Stress per unit strain. And the units for that is pascals. It's the same as the units for what? For pressure. Even pressure has this unit. Then we move. Then we have types of modulus of elasticity. So now we're checking the types of modulus of elasticity, right? Meaning we've got types of modulus whereby we're checking the change in what? In the stiffness of our material. The change in the stiffness of our material, of the material. So now we've got three types as well here that you must know. You must know all of them because they usually ask questions on this and they have a lot of math. Then we have Young modulus, which is represented with Y, we have bulk modulus B, we have shear modulus S. So now let's go to the formulas. So the formula is like that for the first one. Young modulus is the ratio of stress, normal stress to its longitudinal strain. So the formula here is easy. We're talking about the longitudinal. We're checking the length for Young modulus, right? How stiff is that part of our object? We are talking about the book. It means we're checking how stiff was that length. So the stiffness will be checked by the formula, right? So it's Y equal to force per unit area over, don't know what happened there. Okay, let's go back over change in L over L. So that's our Young modulus formula. It's a same mode. And then when you F is force area, it's A, change in length over the original length. Now we have what to call, so obviously this is the manipulated equation, right? So meaning young modulus is Fn over A changing F. It was just derived. I'm sure you know how to derive. Now we'll go to, so you see here they were talking about the radius of a wire. So a wire, its radius is given by pi r squared, a wire, a normal wire that you know. Its area, in order to get the area, check around there. So it's pi r squared. So where there is A, where there was A, you replace with pi r squared. And you calculate your young modulus. So sometimes we can look for the other values, right? So just manipulate. So what you must know here is that every material has its own, has its unique young modulus. That's what you must know. So if the question is talking about steel, you'll just take this. Let's say steel, right? You just take 2,1 and you put it there. You put it where there is y, because it will be our young modulus. If they ask for for you to calculate the length or the force, you're going to just calculate for any of those variables. Now we move. So meaning that you must check your equation when you are. Example one: a spring of 60 centimeters is stretched by 2 centimeters by the application of the load. Uh, so the length, you just collect the data here. We're given 60 centimeters stretched by, I think this is the change in length, 2 centimeters. Mass of our object is 0.2 kilogram. We have to convert that to kg. Calculate the length when a load of 500 grams is applied. So they want the length. So let me just check. So they are looking for change in length. So these two, I'm not sure what is it. This two is what? 0, 0.6, 0.02. Yeah, change in length is going to be 0.02 meters. You convert that. And then this one will be 0.6 meters, right? Now let's go down to these calculations and see, because all the values they were given, and they're talking about a spring. Let's talk about the normal spring. For the total length is okay. So what you have to do is just to substitute everything, right? That you are given. So let's talk about spring. So we know that force is equal to what is mass times area. So this is the for F, and then this is the length that was given. This one is the change in length. Then A is the area of our material. So we're not given the what. Why are we having two objects here? Y equal to 200. Oh, we're having two objects. A spring of what is stretched by the application of the load 200. So when a load of 500 G is applied. Okay, now it makes sense. So what you're going to do is you are going to have two equations.